stuff. Okay. In that picture, though, what is like the whole point of X-ray crystallography? What do we want to know? We want to know the structure, we want to know the atomic positions, but what does crystallography actually get us? It gets us an electron density map. So what we have to do is we have to figure out, based upon this stuff, how do we actually get to an electron density? So, yeah, go for it, Joe. What part of this is solids right now? Yep, this is all solids. The surfaces we're not going to touch until the third part of this course. What was that? Yes. yeah. We're gonna be bumbling after the first exam. I think it's a lot of fun. And we're gonna use math and intuition to build that even better. So now we're gonna talk about the electron density and something called the structure factor. So the big question we want to ask is how do we get a density? Because that's what we're getting out of electron or X-ray diffraction. But we need something called a structure factor to do so. And we need a lot of them. We give it the symbol FHKL, and what's the HKL for again? Yep, those are the Miller indices, so we have different planes we're looking along, and we take a collection of these guys, divide by the volume of the unit cell, and we get a density. Okay, so we need that, and recall that each atom scatters in the HKL plane. With the following formula. F sub n times e to the what? We used phi. We want, yeah, that 2 pi h, u, and we're going to put an n under here because for that specific atom, because soon we're going to talk about a big collection of atoms, plus k v sub n l w n. Okay. So now the question becomes, that's for an individual atom. What if we want it for the entire unit cell? We're going to need a series. So we want all of the atoms, right? Yep. We need a summation, F sub n times e to the I 2 pi hun plus kvn plus lwn. And we go up to a larger n. And this whole thing together is our structure factor.
Is it a true series or can we make it an intro? That's nice.
We're going to leave it alone as a series. Okay. But I see nothing experimental here. Where the experiment comes into play is related this way. Peak intensity, which we're going to give the symbol IHKL. is proportional to the absolute value of HKL squared. So we get intensities out of an experiment. This is a proportionality symbol, meaning they're related to one another. The true expression for this, which I don't want to spend a lot of time on all of what these properties are and what they mean, because that would be important for grad school, but it's not really important here. And I just want to get to my examples so you guys can do them over the exam. Okay, but this is the equation that relates them. This is a scaling factor that depends on experimental parameters. L is a Lorentz factor, which and this polarization factor, which both depend on the reflection that you're shooting at. Then you have an absorption correction, so some of the scatteredness, it isn't completely elastic. You have to deal with that. And then there's something called the multiplicity factor that has to deal with how many planes are you actually hitting this way. Okay. Yes. Trace off the top of your head. The important thing to know is the intensities that we observe from experiment are proportionally related to the absolute value of the structure factor. That absolute value causes problems, which you guys are going to investigate for your daily problems in that reading next week. Okay. So we have this. Let's talk about how do we actually use this. Jeez. And we're going to go through 3 examples that I think are very... Yeah, I'm not going to erase that part. So question, when do we use this thing? So the instrument collects a ton of structure factors in 3 dimensions and determines this. We're going to look at it in a simpler guise and consider reflections from powder diffraction. Let's consider 3 examples. And you guys have these 3 examples. We have polonium, technically alpha-polonium. It is a primitive cubic. Lattice, so that's the one that's in blue and looks like a primitive cubic. We have tungsten, which is a centered cubic. And we have cesium bromide, which is also a primitive cubic. Okay. Oh, no, why'd you shut down on me? I need you more than ever. Damn thing. Sign back in. Delete my stuff too. I changed my password. Tungsten's a very interesting one. Highest melting point. Yep. I don't know about that one.
I just like how dense it is. The intensity of it. The rods we got.
Okay, we're gonna pull this up. Am I okay to pull this down? Okay. Lily, can you check on there to see like how much space I have? Like, can I write over here or do I have to write over here?
You can write like where those are listed, and you can write until like on the graph.
Okay, so I got space. Okay, let's pull this stuff up again. Let's see, maybe it's still in the downloads. I doubt it. Nope, empty. Okay, we got to log back in. I know.
We should break it and then break it through.
There we go.
I talked to Kyle about it. He said I could.
Oh,
Yeah.
oh, in the library.
Yeah. He said just don't go in.
Okay, let's see. Download. Download.
10 minutes of laughter for 10 minutes for 10 years.
It's worth it.
Exactly. Not like I'll do it.
Please don't encourage them.
Okay, polonium, here we go. About time. Of course, you can't see anything, so we'll turn that on. Word's taking forever to boot up. Turn that down, does that help? A little bit. Close, I don't care about privacy. Microsoft doesn't care about privacy. Are you kidding me? View. Switch windows. Can I make it full screen? This is fine. Oh. Which one are you working? No. Next one. Press 1. Unless someone disconnected the computer. There we go.
Whoa.
Too close. Okay. This is alpha-polonium. Named after what country? Yeah, Poland. I think it was discovered by Marie Curie, but I'm not too certain of that one. I just assume it is because it's Poland.
Mercury?
No, polonium. Okay, so now this is our unit cell up in the corner. How many atoms are contained within one unit cell? One total atom. Yep, on all corners, but technically, where is the center of one? In the corner, at the origin. So what would the fractional coordinates of this guy be if it's at the origin? U would be equal to 0. V would be equal to what? Yep. And then W is equal to? Great. Okay, let's write out the structure factor. Oh, yep. Okay, the structure factor, HKL, is equal to the summation of all the elements or atoms within the unit cell. How many atoms do we have?
Just the one?
Yep, it's just the one. And we have a special index. We should indicate what element it is. And then we have e to the I 2 pi. And then we would normally have h times u plus k times v plus L times W. Yes, it is going to be good. This one's a nice one. So H times, what's my U?
0.
Yep, plus K times my 0 plus W times my, yeah. E to the 0 is what?
1.
So we just get the structure factor or atomic scattering of polonium. So FHKL, we got to take the absolute value of that, is just equal to this thing. Okay, so now as we look at these reflections, let's see if we can try to find what's happening here. So we don't have any for the 0, 0, 0. How would this change for the 1, 0, 0? So there we would lose a bit of this information. We would have a 0 here, e to the whatever. So that's why we see 1, 0, 0 along here, is it appears. And if you look, you can see all of these reflections as we plug those values in. Now their intensity matters on how many times we can make that. So this is not only representative of the 1, 0, 0, but also the 0, 1, 0 plane and the 0, 0, 1 plane, right? Okay, not too exciting, but it's there. Let's move on to our next example of tungsten. So if we look at tungsten, and I can switch between the two. Yep, W. Now, if we look, what do you notice has changed between them? There's 2 atoms. What about the diffraction? There's no 1, 0, 0. There's no 1, 1, 1. What is going on here? Let's try to use our logic to go a bit further. Okay, next, tungsten. How many atoms in the unit cell? 2 atoms. Okay, where's atom 1's position? Fractional coordinates of U, V, and W, all at what?
0.
Yep, that's what I would pick because it makes the math easy. And atom 2 is in the dead center of that unit cell, right? So what should its fractional coordinates be? Yep, 1/2. I'm gonna just write 0.5. Okay, the structure factor. Now, we don't just have 1. How many terms are we going to have? 2. And the reason we have 2 is why? Yep, 2 atoms in there. We have F of W1 technically, but the structure factor should be the same for each of them, times e to the I pi, 2 pi. And what's the total thing going to be for the first atom, given it's at fractional position 0, 0, 0? Yep. Plus e to the I 2 pi. Yep. 0.5 h plus 0.5 k plus 0.5 w. That's going to simplify further into what? If this is all 0.5 and we're multiplying it by 2? Yep. And that's what we arrive at. Okay. I'm going to blank this for a second. Can I press B to blank it? Nope. Okay. How are we doing on time? Okay. We're not done with this one yet. Okay. Now, we don't run into a simple situation in this case where it's just the same. We now have another term that we have to worry about. Okay, but what do we know about H, K, and L? They don't have to be equal. They're whole numbers. Yep. Since H, K, and L have whole numbers, That means there's a limit to the values that they could have. We're going to look at an example where we consider e to the I pi h plus k plus L. Okay, for the 1, 0, 0, what happens to this part of the expression? This bit here. For 1, 0, 0. E to the what? I pi. Okay, yep. And that is equal to, using Euler's equation, cosine plus what else? Pi. Okay. Cosine of pi is equal to what? 1?
Oh, wait. No, sorry.
Not 0? -1, yeah, there we go. And sine of pi is 0. So plus 0. So this gets us a -1 value. Okay, what about 1, 1, 0? What happens there? We get e to the what? I 2 pi, which really means cosine 2 pi plus I sine of 2 pi. Okay, cosine of 2 pi is what? 1. What about sine of 2 pi? Yep. In that case, we get a +1. Okay, we're going to do 2 more of them. 1, 1, 1. E to the I what? 3 pi, which really means cosine of 3 pi plus I sine 3 pi. 3 pi, what's the value of that going to be? -1 plus 0, -1. Are you guys seeing a trend, or do you want me to do one more? Okay. For even h plus k plus L, this e to the I pi h v hu plus kv plus lw, what's its value going to be for even, given what we've done here? Yep, it's going to be +1. For odd, what's it equal to? Okay. So this is our structure factor, right? So my question is, will the 1, 0, 0 reflection show up? There we can go back to our structure factor, 0, 0. We got first the atomic scattering factor of that tungsten at the origin, plus our other tungsten E. So if we put in 1, 0, 0, what does this whole term become up here? I pi, yep. Which we just showed is equal to what? Yep. So we get this. What's the value of that? 0. And since the structure factor is squared is related to the intensity, should we see a reflection? No. Okay. Now, let's ask the same question. What about the 1, 1, 0? So F1, 1, 0 tungsten plus W. E to the what for the 1, 1, 0? I 2 pi. And what does that work out to be? Yep. Will we see a reflection there? Yes. So now, I'm going to pull this thing back up. So we said we won't see one at the 1, 0, 0, but we will see one at the 1, 1, 1. Let's look at our powder diffraction. Look, oh, we should see the 1, 1, 0. We do not see the 1, 0, 0. And if we look, these guys all work out to be evens. Right, exactly. Now, what I'm going to have to cover on the interwebs is this. This is cesium bromide. It has almost the same structure as tungsten, but the center atom has been replaced with a bromine, and the origin atom is a cesium. In that case, we do see the 1, 0, 0 and the 1, 1, 1, but they're very weak. So watch that video and we'll explain why that happens. Okay?